Good afternoon. Welcome to this second live session for the course Computational Fluid Dynamics for Incompressible Flows. So, if you have any questions or doubts, you please post in this chat box. We will discuss and we will try to answer. So please post your queries in this chat box. So in the meantime, let me discuss this question. So one question was asked that why even order derivatives in the leading truncation error results in dissipation. So you have already studied in the course that for this equation, where C is the wave speed, so you can see that if you have some wave like this, so in the truncation error, if you have even order derivatives, then we can see that this amplitude, there will be amplitude errors and you will get like this. So you can see that this cause numerical dissipation. So this is dissipation error. So this comes for the even order derivatives in the truncation error, and this is known as smearing. And if you have this wave, and if you have odd order derivatives in the truncation error, then this will look like okay. So you can see there will be wiggles, okay, and this is known as dispersion error. Okay, so you can see that dissipation error occurs when the leading terms in the truncation error have even order derivatives and they are characterized by a loss of wave amplitude. Okay, so we get amplitude errors, and you can see that it has strong amplitude error but little phase errors. Whereas in dispersion error, you can see that it occurs when the leading term in the truncation error have odd order derivatives and they are characterized by oscillation or small wiggles in the solution. So you can see that these are for waves of different wavelengths propagate at different speed, so we will get these wiggles. So obviously you can see that it has a large phase error but little small or amplitude errors, So to analyze why this happens, so you need to do the this von Neumann stability analysis, and you need to do very rigorous mathematics. Then you can say, but you can see that there is a error in the amplitude. Okay, so that causes the dissipation error when we have the odd order, sorry, even order derivatives in the leading term of the truncation error. So if you have any other question, you please post it here. So we'll wait for another 2-3 minutes. Okay, you please post your queries. If you do not have any doubts or queries, then we will leave within 2-3 minutes. Please post your queries in the chat box. So another question: how can we better avoid the dissipation error? I think it is reducing time step and grid space, isn't it? Yes, so because it depends on the truncation error, and you know that if we decrease the grid size and the time step, obviously truncation error tends to 0. So, but you can see that if truncation error tends to 0, then obviously this error will be means smaller. Okay, but there will be this type of error present, but its magnitude will be less. Another question is that which one causes more error, dissipation or dispersion? Say these are two different types of error as we discussed. Okay, so one gives the smearing error, another is in the Wiggles form. Okay, so and both together those are known as diffusion error. But anyway, in the leading order term is dominant in the truncation error, and this will lead to means more errors either in dispersion or dissipation. Okay, so both will be present, but as I told before that if truncation error tends to 0, then obviously its effect will be less. Okay, so we'll wait for another 1 minute. So if you do not have any question, then we'll end the session. So if you have any queries, you please post in the discussion forum. We will just give the answer, and uh, you just if you have any other doubts, you can also email personally to me. I will try to give the answer. Another question, sir, how can we apply boundary condition for 3D rotating cylinder for a laminar range? So if it is rotating cylinder, then if there is no transverse direction velocity, then you can see that no slip boundary condition should be applied at the cylinder surface. Now, what is no slip condition? So whatever velocities will be there of the cylinder surface, that will be the fluid particles residing on the surface, it will have the same velocity. So obviously you can see that if it is rotating, then it will have two components. One is tangential velocity and one is normal velocity. So normal velocity you can make it zero, because if it is not traversing, so it is only rotating. And tangential velocity, you can see that it will be just omega into the radius of the cylinder. Okay, so obviously if you are using cylindrical coordinate, then obviously it is easy. However, you can transform it into Cartesian coordinate, and accordingly you can give the boundary condition. So another question is there. I have only used the current number, but in some cases I have run simulations with current number 5 and it worked. How is it possible? Other phenomena was more important. Can you please clarify which problem you are solving when you are giving current number 5? So say if it is obviously if you are doing the von Neumann stability analysis, and you can see there will be some stability criteria, right? In some cases, if you are getting results, but you have to see whether that is physically correct result or not. Okay, you might get some results. Okay, but those results, whether it matches with the analytical solution correct, exactly or not, that you please check. Okay. So this is Jayant has asked one question. So this is not related to this subject. Okay, so you can inquire in the concerned office. So you can see that in means as I told before that Quran number 5, if you are getting results, I do not know, you just check the from the Vonderman stability analysis, what is the condition. So anyway, means it depends on that, means uh, your this wave speed, whatever speed you are getting. So it depends on, means the time step uh, and the means grid size. Okay, so current number depends on that. So you can check. I do not know exactly your answer. Okay, so that I have to check for this problem, and I can, then only I can answer. Okay. So another question is that that what is the physical significance of Courant number? Okay, so that you can check from its definition, because you can see that Courant number is defined as C into delta T divided by delta X. Okay, so obviously you can see that when the wave this wave speed, okay, you have to choose the speeds or delta t such a way that it should not pass, or it should not cross a single grid spacing fully. So it should be within that, then only you will get very correct result, right? Say if you just imagine, say one fluid flow phenomena, let us say that one fluid drop, let us say rain drop is falling under the gravity on the pond. So now you can see that when this drop is falling, this, it is a very fast phenomena, right? So you have to choose delta t such a way that you will be able to capture the physics of the problem. So similar way, when you are defining the Courant number, so you have to choose delta t or delta x such a way that this fluid particle, okay, it should not pass within this unit time in a unit this grid spacing. It should be within that. Then only means you will be able to capture the physics, right? Okay, so if there are no questions, again we'll meet in the third live session. If you have any other doubts, you please post in the discussion forum. Okay, thank you very much. So we'll end the session.